We're 3 minutes past your call, I think. I don't see a lot of people joining. There's 1 or 2 more people. People are joining. Maybe wait 1 more minute and then go ahead. Yeah.
Okay. Great. So I checked my design capabilities with this page.
Looks very impressive.
Thanks.
Have you applied ML to design it? If not, you need to redesign. We need ML.
Yeah. It's like the old logo from Intel, Intel Inside. Everything I do, I have a small logo. You cannot see it, but it's ML inside.
Okay.
We'll wait for another minute and then we start. Okay, so good morning, good afternoon, good evening, wherever you're in the world, and in Israel, Shabbat Shalom. I'm honored to open the 5th and last day of MLCAD this year with a panel with ML4CAD, where is the treasure hiding? We have 5 great panelists, which I guess you already know in the community. With us, we have David Penn from University of Texas, Austin. We have Mark Wren from Nvidia Research. We have Manish Pandey from Synopsys. We have Marilyn from University of Nebraska, Lincoln. We have my friend and colleague Raviv from IBM Research Haifa, and I'm Raviv Gal, also from IBM Research Haifa. So we will try to be a little bit provocative and ask, ML is has been able to revolutionize areas like image classification and NLP, and ML and CAD seems like a perfect match. And we have many works in academia, industry, and tool vendors, the best of them. Success stories and work in progress were also presented in this wonderful workshop. But I would claim that the ML4CAD revolution, where ML shake or take CAD to the next level, has not been arrived. And we will try to, I will ask, and then the great panelists will try to answer the question, where is the treasure hiding? And we will try to answer questions like, do we just need more time? Or is it a matter of finding the right ML means for CAD? Or are CAD problems fundamentally hard, even for ML-based solution? Or is it difficult to improve a very mature and highly automated areas like we are working on? Or is it with most of the data owned by chip companies? Is data availability a major blocker? Or are there domain-specific characterizations that require further advances in ML? So we have the great panelists, I think, to try to answer these questions. And I think that we will start in the random order that I invited the panelists. So David, I will invite you to start, and let me just introduce you in a more fashion way. So David Penn received his BS degree from Peking University and his MS and PhD degree from University of California, Los Angeles, UCLA. From 2000 to 2003, was research staff member with IBM T.J. Watson Research Center. He's currently a professor and holder of the Silicon Laboratories Edward Chair in Electrical Engineering at the University of Texas, Austin. His research interests include electronic design automation, design for manufacturing, machine learning, and hardware acceleration, design CAD for analog mixed signal design and emerging technology. He has many publication papers and many awards, including the CRC Technical Excellence Award in 2013, DAC Top 10 Author in 5th Decade, and many more. And he served as a Senior Associate Editor for ACM Transaction of Design Automation, Electronic, and many more. I think that we want, David, I apologize for not going for the full list because we wouldn't end. So the stage is yours.
Well, Raviv, thanks very much. I mean, bio is thanks for your introduction. Can you see my screen?
Yes.
Okay. All right, let me start. Well, thanks, Raviv, for your kind introduction, and thanks for other distinguished panelists. It's my great pleasure to be here to share some of my views on machine learning for CAD. Where is the treasure hiding, right? Before I start, I think, to my view, right, machine learning really for EDA serves as two kind of toolbox, right? One is kind of like more hammer to tackle each step. You know, we know that nails and hammers, right, to make each step really better, right? You know, better quality of result, faster turnaround time, and so on and so forth, right? So for each of these, I mean, here I just used some physical design as an example, but you know, the hammer can be applied to verification, to synthesis, and whatever, right? And meanwhile, we have also heard about, you know, I think machine learning can be used as some kind of bridge to, you know, to connect all these different design abstractions, and or even hopefully bypassing some of these steps, and so that we can directly achieve some final results that we want, right? I think this is what I'm kind of thinking for the two kind of takeaways, right? So one is really to like hammer each step, getting them better, faster, and another is to kind of serve as a bridge, right? Just as a hammer example, right? So in terms of placement, right? Recently, we published the paper. This is actually in collaboration with Hao Xinren. He's also a panelist here, my former PhD. You know, we kind of like look at the classical nonlinear placement problems through a new angle, like using some kind of analogy with neural network training. And by doing this, we actually can hammer out and get a very high quality and ultra fast. And meanwhile, the development effort can be much lower compared with previously if you want to write some placement from scratch, right? We leveraged a lot of the hardware, machine learning hardware and software, and also it is extensible. So this is just some kind of example, like, hey, you know, let's kind of revisit some of these classical problem from like a deep learning kind of angle. And hopefully we can, you know, get each of these steps much faster and still with very high quality results. And in terms of the bridges and also some kind of more bypassing some intermediate complicated steps, right? So there are a lot of works people have already talked about. I think this is probably one of the most successful user cases of machine learning, you know, to predict, to classify, right? Whether you have hotspots, you know, for lithography, for reliability, or, you know, thermal, whatever, right? Routability, DRC, or hopefully even we can even do post-routing timing analysis, right? So that kind of matching is very, very important, right? But meanwhile, right, so even without going through this kind of, here is just another example that we have done recently, right? So basically, right, we know that lithography and the simulation, those are the really, really expensive. And what we are looking at, okay, so if we don't do any of this kind of physics-based simulation, can we directly get some final printed image which will be shown in the fab, right? So that's why I call it kind of end-to-end kind of modeling, right? Using some generative adversary network, right? So again, we have shown some really exciting results, right? So basically, you give me some input mask kind of clip, and I can directly tell you the printed image, right, for the features that you care about. And so with really similar quality of results, but you are talking about thousands of times faster, right? So here are just like two takeaways. And so what I'm thinking is that, as researchers here and a lot of, young students, I guess, so we need to dream bigger, right? So, on one hand, right, can we have more dream type of paradigm to revisit those classical EDA problems, right? So not only just placement, right, but maybe for other critical steps, we know that routing is really, really hard, but it's kind of hard to formulate into a more, nonlinear kind of optimization problem. But hey, maybe we can revisit some of these problems and the sizing and so on and so forth, right? So another thing that we really can dream bigger, which is like kind of also my wild dream, when I discuss with Mark and inspired by some of our discussion with the Nvidia friends, right? So essentially, right, currently, right, most of the success in the kind of machine learning is more in the prediction, right? Can we even use machine learning to do implementation, right? So maybe even bypassing many expensive and iterative steps, right? And for example, directly from some layout to final netlist. I mean, this is really a super wild dream. I don't think it is possible yet, right? But this is something to think about. Now let's come back to the questions that Raviv asked at the beginning, right? So where are the treasure hiding, right? So do we simply need more time to identify problems of which machine learning can change the game? I mean, of course, right? So definitely, right? I mean, for EDA, we always have many challenges and other problems, right? From PPAs to manufacturability, reliability, turnaround time, right? So I think we need to identify the critical paths and the components in this kind of design flow, right? And see where machine learning really can be a game changer, right? So I think from this this conference, right, there are many great keynotes and many invited talks. I think folks have already identified a lot of critical paths, right? We just need to find better ways to solve it, right? So that naturally leads to the next question, right? So where do I find the right ML methods, right? So there are many machine learning techniques from, this is the most widely used, right? Supervised learning, right? But then there are also a lot of, areas like unsupervised, we have so many data, which are not really labeled, right? And not even structured, right? How to maneuver this designer data, right? And between them, there's also semi-supervised. If you don't have so many labeled data, but with massive unsupervised data, so I mean, unlabeled data, how we can do that? And even, of course, reinforcement learning has become very popular nowadays, right? And so I think we do need to find CAD specific and CAD application specific machine learning, right? Because a lot of the mainstream machine learning algorithms were developed by the image classification, computer vision, and the natural language processing, those communities, right? The data more or less maybe they are more flat and and stuff like that, right? So, but for chip designs, right, we are always changing, right? We have 7 nanometer to 5 nanometer and 3, and and then there's a new FinFET, there's new whatever, right, structures and get all around, right? So also, right, when you are moving to a new technology, you don't really have that much data. So we always have a big data versus small data problem, right? So how we can make our machine learning to be adaptive, right? So yeah, indeed, right, CAD problems are fundamentally hard, right? So I think there's no question. I think we have many folks who have been working in this community, right? So they're highly constrained, so many design objectives, constraints. And we are talking about, the importance is very important, right? So your design ultimately has to be, LVS clean, DRC clean, right? And meet all your timing, power, and all these specs, right? So, we have so many like continuous versus discrete, right? So you cannot just do continuous optimization, but ultimately you have to map them to your standard cell library, put them in circuit rows and stuff like that, right? So there are many hidden structures, hierarchical design, etc., right? So I think, right, maybe we should try to kind of, on one hand, there is like for machine learning community, we can kind of educate them. Hey, look, we have so hard problems, please help us, right? Because they are, conventionally looking at for other more like a, image or language type of problems, right? And on another hand, right, so basically we need to extend those to consider those kind of abstraction and stuff like that, that is CAD specific, right, chip design specific. But on the other hand, maybe we can also, from a CAD perspective, maybe we could revisit some of the abstractions in the age of AI. I mean, so this is, again, an open question. All right, so the next question is, what is the difficulty to improve already highly optimized areas using cutting edge technologies, right? I mean, I think I would still like to go back to this kind of dream place type of example, right? So I think, yeah, indeed, right? I mean, EDA problems have been studied for 50+ years, right? We have tried to really use all kinds of knobs, right, to do optimize, whether it's heuristic or whatever, some graph theory, etc., right? So there's a lot of algorithms, right? Heuristics or more like provably, optimal algorithms. But meanwhile, with AI, right, so we do now, there's a data-driven type of approach, like how we can get the best of the two worlds, right? So that's actually something I think we can think about. Well, regarding the data, right, that's a problem, right? So data is always a problem. So, usually, right, I mean, academia, we are the, I think, probably lowest in the food chain. We don't have real design data. EDA companies has more, but, real design data are all in these design houses. They probably don't want to share, right? So I think there's recently this open source movement, right? For example, Open Road, right, from UC San Diego, and from my research group, we also have released like an analog layout tool called Magical, right? We also, based on the Magical, because it's fully automatic and very fast, we can generate a lot of learning data. We actually even released this, right? So I guess with open source data and all this, right? So we probably can develop some kind of model which may be more or less generic, right? But of course, once you apply to your chip company, and you still need to adapt it, right? Or even EDA companies model, right? Probably once they apply to real design, need to be adapted. So yeah, last but not least, I think there's the last question, right? You asked, right? Are there domain-specific characterizations that require further advancement in ML? Yeah, definitely, right? Chip design and EDA are historically not the mainstream of ML advancement, right? So we do need to consider many things, right? So which hierarchical structures and hidden constraints, and whether we can have maybe even for generative, right? So I kind of showed some example like litho gain, right? So can we now even do for that super transformer, like from RTL, something like that, to the final, layout, right? We may need some bigger transformer or more generative learning, right? Which not only is the image, but also consider structures or graph, consider all these other things like timing, power, or other chip design specific notions, right? So again, right, I think that really needs a collaboration between two communities, right? Okay, I think I will stop here. So thanks. How do you want to proceed? We'll leave all the questions at the end.
Yeah, we will make a first round where each of the panelists will have an initial statement, and then we'll open the room for questions from the audience. So our next speaker will be Mark Wren. I hope that I will pronounce it correctly, Hauxiang. Not sure. So Mark is a principal research scientist at Nvidia Research. His current research interests are machine learning application in design automation and GPU acceleration EDA. Before joining Nvidia in 2016, he spent 15 years at IBM working on physical design and logic synthesis tools and methodologies. By the way, I was not aware of the IBM connection either from Mark and with David. So I was surprised. He received many IBM Technical Achievement Awards, including the IBM Corporate Award for his work on improving microprocessor design productivity. He holds over 20 patents and co-author of 40 papers, including several book chapters on physical design and logic synthesis. He has received the Best Paper Award from ISPD and DAC. He's an IEEE senior member and serves as TPC member for ICCAD and DAC. He earned a PhD degree in computer engineering from University of Texas at Austin, MS degree in computer engineering from Rensselaer Polytechnic Institute, and the MSBS degree in electrical engineering from Shanghai Jiao Tong University. So, Mark, stage is yours.
Okay, can you see my screen?
Still,
Can you see my screen?
Yes, now we see it.
Yes. So yeah, sorry for the confusion. My legal name is Hao Xinren, and I goes by Mark. So you can call me Hao Xin or Mark. I mean, take whatever you prefer. It's all me. Okay. So title of my little slides is from alchemy to algorithms. So I think machine learning has made a lot of head news and headlines, and also we have used the machine learning applications in the CAD community. I think there's three major categories which aligns well with basic machine learning categories, right? We have predictors, which is like basic supervised learning, right? We can predict congestions, timing, IR, power, testability, and you name it, right? We can predict. Of course, reinforcement learning, we can use that as an optimizer. We can do micro placement, from Google's work, and a lot of works that, in this workshop use reinforcement learning. There's generators that also David talked about. We can do OPCs, we can generate congestion map, and so on and so forth. So, well, the problem is, there's still a lot of challenges to actually, use this machine learning techniques in real work, right? I mean, there's a lot of papers and a lot of projects going on, but just like the title of this session, despite all these success stories, this revolution is still not yet right? And the reason is like this challenges, right? The challenge is like, these models all require a lot of data to train, right? And and there's like a training and inference distribution mismatch, right? Because you never know you have enough data, and once you inference that there's a mismatch in your distribution, then your model by definition will not work. So I think we're kind of in the stage of don't know why and how it works, and this is not just me. It's I think it's a lot of people in the machine learning community. They talk about this, right? Alchemy is like the word. There's a huge debate going on. I think a lot of time we just like cross the fingers and hope it works, right? Especially in inference. So I think that's kind of the state of the current state. So I think that let's look at the algorithms, right? Traditional CAD algorithms, and we have so many algorithms. We have synthesis, placement, routing, buffering, and even like inside each step, there's like many different algorithms. And there's many good things about the algorithm, right? So algorithm works on any data distribution, right? I mean, if you have a placement algorithm, it's supposed to work on all the placement. It doesn't maybe not give you the best QOR, but it gives you something, right? So algorithm can generate data, right? You run it, you can generate something, and it would give you more data. And we know how algorithm works, right? We have studied for 50 years, we know how it works. So but there's challenges, right? Algorithm it's this increasing design complexity. Like in the industry, like run a backend design flow will take like a week, right? For a block with like 2 million cells. So it's quite slow, and we still want to improve the QOR. We want to improve the runtime, and this is cross-stage issues, right? Because algorithms are like they run one step at a time. But the assumptions of the environment keeps changing, right? When you have CTS, you have post out, it keeps changing, right? And this cost stage, right? And it's just not able to optimize anything that's like, a few stages later. So that brings us to the idea of integration in machine learning and algorithm, right? In other words, data-driven algorithm design. I think a lot of speakers in this workshop talk about this as well. I just want to echo what they're saying. I just want to give basically 3 examples of how to do this, right? First, you can use machine learning as some sort of oracle within the algorithm, right? Like A star, which is like a maze routing algorithm, which has an oracle, right? So you can use machine learning to replace that oracle, right? Make it better. You have these heuristics in the algorithms such as like ILP, right? When you make decisions on how do you choose branch and bound variables, you can use machine learning to do that. So that's one way, right? Another way is you can use machine learning to drive algorithms, right? So, you can choose, basically use machine learning to choose which algorithm to select at which step, right? Such as you have synthesis transforms, so many transforms, which transform you choose, right? Or you can use machine learning to select parameters, right? Recently work on like choosing the clock tree synthesis parameters using machine learning, right? So that's another way. And the third way is like you can compose machine learning algorithms, right? So make them both, machine learning and the algorithms are kind of like a component of a bigger algorithm, a bigger tool, right? So part of the bigger problem algorithms. And I'll give you an example in the next slide. And there's more research can be done. This is answer this question. We think that there's a lot of research can be done in this area, lots of them. So this is just to give you an example of how do we combine machine learning and algorithms together to solve to form a bigger algorithm, right? And this is a latest work from our group. So we're talking about how do we generate the standard cell routing, right? This is not about the routing on top of the cell; it's the routing inside the cell, right? How these cells become very complex, it's very big, and there's a lot of DRCs. It's very hard to handle, right? Because this is a front end of line, the middle end of line. This DRCs are much more than the DRCs on the metals, on the top level metals. So to solve this problem, right? So we basically come up with, we have a DRCs. How do we fix the DRCs, right? We use reinforcement learning, right? So basically we leverage both genetic algorithms and the maze routing algorithms to come up with, a routed design. But DRC is not fixed, right? So we use reinforcement learning to fix the DRCs. And then the maze router and the DRC fixers will all feedback the numbers, like how many nets are unrouted and how many DRCs are remaining back to the genetic algorithm. The genetic algorithm uses it as a fitness function to basically iterate and until it fixes all the DRCs at the end, right? So this actually works pretty well. And when we use it, this RL training agent, we just train it on like one single cell. And it learns to fix these DRC rules for all the cells we have seen in the library. And in fact, we can actually pretty much down like 90% of the cells in the library. So it's pretty interesting results. So when I think about alchemy and algorithm, this is the picture I have in mind, right? So, we really want to have modern machineries, right? That's accurate, precise, and efficient, right? So I think with machine learning and the algorithm together, we can build something like that. And talking about the machinery, right? I really want to talk about GPU from Nvidia, right? So I think the GPU is a very natural computing medium for both machine learning and algorithm, right? Of course, it's for machine learning because everybody's training on GPU. But it's also a very good computing medium for algorithms, like we have parallel computing algorithms, right? GenePlace is one of these examples. So actually next year, we're gonna have another, every year we have 2 GTCs, the GPU Technology Conference. And usually it's a lot of people from all kinds of industries, computer visions, healthcare, robotics, and retail. This is, you name it. Anybody who apply AIs will come to this conference and talk about their latest applications. And next year we're going to have a new EDA track, right? There wasn't have any EDA track before, Now next year we're gonna have an EDA track, and we invite everybody, that's interested in applying GPU machine learning, to EDA domain to this conference and submit it to the conference. And that's my talk. Thanks.
Thanks you so much, Mark. And I think our next speaker will be Manish Pandey. So we had one speaker from academia, one speaker from industry. Now we'll have a senior speaker from a vendor company.
All right.
And Dr. Manish Pandey is the Vice President of R&D and Fellow at Synopsys, and adjunct professor at Carnegie Mellon University. He completed his BTech in computer science from the Indian Institute of Technology, Kharagpur, and his PhD in computer science from Carnegie Mellon University. He currently leads the R&D teams for machine learning, distributed system, and formal tools at Synopsys. He previously led development of several static and formal verification technology at Verplex and Cadence, which are in widespread use in the industry. He also has extensive experience in distributed system and computing infrastructure when he led the display advertising security group at Yahoo and storage analytics system at Nutanix. Dr. Pandey has been the recipient of the IEEE transaction in CAD Outstanding Young Author Award, and holds over 2,000 patents and refereed pages. And so Manish, the stage is yours. Looking forward.
Thank you, Raviv. Okay, so let me try and share my screen. Okay. All right, so can everyone see my screen?
Yes, you're
All
good.
right. So actually, great talks, initial introductions by, by David and Mark, and actually this kind of sets me perfectly, right? And, so I think that if you look at actually, EDA, as an EDA vendor at Synopsys out here, right? We see opportunities across the whole design abstraction, right from system level specification to architectural design to verification, all the way down to the mask level, right? And these are innovation both in tools as well as in methodology, right? So tools, it means that you cannot take each of these individual tools, whether it's synthesis, place or route, power estimation tool, or even actually verification coverage tool, or actually a methodology will be something that kind of spans across the different abstraction levels, right? And I think, again, if you kind of look at actually, for examples, for some very specifics out there, architectural exploration actually is a big, is a big undertaking right at the beginning whenever we kind of undertake a new project, then from going down to actually static verification, formal verification, closure, timing closure, simulation, and all the way to silicon engineering. Okay, so these are all the different areas, where ML is a candidate. Okay, and I'm going to skip this here, but if you look at actually of this, right? So the main drivers, right? And again, it's not lost to the audiences, right? You want to get better performance, you want to get higher accuracy, no matter what your algorithm is, faster debug, right? And obviously cost to all of these, right? To reduction of the cost. And I think that my thesis really is that there are two things. One is that across both in academia and in industry, there's been actually a lot of work actually in this optimizing individual point tools. But what I see today actually is that there are relatively few people kind of addressing the problem of optimizing across the flow. And in my opinion, actually, with what I see in the industry, both on the semi side as well as the EDA side, I think that this is a relatively under-leveraged area, right? Where we're not kind of going across from point tools, going to cross flow optimizations, right? There's a lot of link between physical and functional world, right? Fab and physical. And I think that each of these are kind of staying in their own silos. Okay. So that's one of the opportunity and one of the challenges that we all kind of need to kind of take up. But I think that the second problem actually is that, and I think even a bigger problem is that the data and model ownership, I think, is the biggest impediment today, in making progress in this. So, many of our distinguished panels kind of talked about, about individual algorithms. All that is well and good, right? But from a tool vendor perspective, right, or my personal observations, without access to the data from the latest designs, I think that, without the right data sets, I think it's pretty hard to kind of get the latest benefits of there, right? And the second thing actually is then conversely, right? I think that all the EDA tools, right? I mean, I think there are about 100 plus of these kind of generate fairly extensively internal data structures, internal data sets. And these are not, again, openly available out there, right? So this data and model ownership is a very critical thing. So, right? So if one of the tools kind of generates the model, who owns the model parameters, right? What are the hyperparameters? How do we kind of tune it? So we talk about all this nice work and nice research work, but without kind of this kind of, without having an appropriate model for data and data sharing and model sharing, I think that we'll be fighting this battle for a pretty hard time. We are not yet actually at the image net moment for EDA, right? And take any one of the single domains, right? Take the verification domain. So we don't have, again, we are working on it, right? But to have that scale of publicly available data, that scale which kind of helps address, let's say we take even a single problem, like in coverage out there, right? Coverage alone, right? Verification coverage is about $1 billion problem, right? That's the amount the semi industry, spends in kind of making sure that you get kind of design coverage, right? Now, we don't have the kind of data to kind of make this go. So this is, I think that, in my opinion, needs close collaboration between industry and academia to come up with appropriate ownership models so that we can kind of make progress out here. Addressing actually to Raviv's question, actually, that do we need more time to identify the problems for which ML can change the game? I think that, I think not. I think that we have a pretty clear idea, actually. We have about 50 plus projects kind of going on in Synopsys. Actually, most of them fairly successful. A few of them actually in the second or third rev of the algorithms, where we know actually where exactly do we need to kind of change or do out there, right? Is it a matter of finding the right ML for the CAD? I think that's a great question, and yes, I think that we employ actually assortment of supervised, semi-supervised, unsupervised, and even kind of deep reinforcement learning for these problems, right? Many of our panelists talk about some of these algorithms. So we can, I think that, we have lots of smart people in the academic industry, and we are kind of, every day we are chipping away at the problem. But, the good thing is actually that there's a vast amount of, work that's been done, and then we need to kind of, for vision and in natural language processing, and then we need to kind of find ways to kind of bring these algorithms onto a domain, right? For example, right, for analyzing sequence of data, right? And, an LSTM, for example, would be a fairly natural way to kind of process it, right? And I think that in the last couple of years, right, with this transformers, right, using transformers to analyze long sequences of data, I think seems to be a fairly natural fit. So we have to kind of understand, and I think that many of us kind of do, right, could take these problems and ideas from a different domain and translate this down into our world, right? But I think that, but the main thing again is that the data kind of becomes kind of an issue out there, right? Now, other question actually is that, is it difficult to improve an already highly automated area using cutting edge technologies? Actually, by the way, ML actually has been in use in EDA, even if we have not called it ML, right? If you look actually fab data analysis, right? PCA has been actually a mainstay of analysis for, a couple of decades now, right? And of course, the volume of data we can process today is kind of much higher. So, and I think we kind of see this opportunities where it's hard, but we kind of see that by employing some of the modern ML algorithms and some of the modern large-scale data processing methods, we can kind of be very successful. Okay. I think that the next question actually was that if the data is owned by chip companies, is data availability a major blocker? Yes, it is, I believe, a big blocker. If you look at actually the higher up the abstraction level you go, the bigger the problem it is. The lower down the abstraction stack you go, right? The laws of physics, the laws of electromagnetism, right, kind of govern things. So I think to some extent you can kind of generate synthetic data that'll be fairly realistic. But going up the stack would kind of require more data exchange, right? And I think that are there domain-specific characterizations? I think that, and in my opinion, not really. I think that these problems kind of, other than what abstraction level you're working on, these problems kind of span fairly well across different design domains. Okay, so that's all I have.
Thanks a lot. So thanks a lot, Manish. And our next speaker would be Marilyn Wolf from University of Nebraska, Lincoln. Marilyn is Elmer E. Koch Professor of Engineering and the Chair of Department of Computer Science and Engineering at the University of Nebraska, Lincoln. She received her BS, MS, and PhD in electrical engineering from Stanford University in 1980, 1981, and 1984, respectively. She was with AT&T Bell Laboratory from 1984 to 1989. She was on the faculty of Princeton University from 1989 to 2007 and was a former distinguished chair at Georgia Tech from 2007 till last year. Her research interest included embedded computing, embedded video and computer vision, and VLSI systems. She has received the IEEE Computer Society Good Memorial Award, the ASCE Terman Award, and IEEE Circuit and System Society Education Award. She is a fellow of the IEEE and ACM and IEEE Computer Society Golden Core member, and also part of the originator of this wonderful event. So Marilyn, stage is yours. You're on mute. You need to unmute.
Thank you so much. Good to see everybody. Greetings from the hellscape that is the land of 28% positivity. So, I'm gonna not put this in presentation mode because it doesn't always play well with Zoom. But let me provide some random thoughts on various topics that Raviv put out. Part of the job of a panelist is to be at least somewhat controversial. So let me say as to where ML machine learning will benefit CAD the most. My guess is at the ends of the design process, right? So device and circuit characteristics are very complicated. There's some interplay between sort of physics and perhaps multi-physics with discrete optimization. Very complicated, lots of subtleties. Seems ripe for we would hope that machine learning could ease the burdens of doing some of this stuff. At the other hand, when I mean system design, I mean when you're dealing with billions of transistors, right? So this could be physical design, timing, and so forth. Lots of complexity, and also to the extent that you are designing, taking into account end use cases, it's complicated. Certainly the synchronous methodology gives us a big leg up in what we have to analyze. But I will argue in a minute that I think we need to pay more attention to use cases. So at both ends, we've got lots of intersecting issues and a whole bunch of things. And in the case of devices and circuits, ultimately, think of electrons and atoms and things like that. In the middle, logic design, transactions, and so forth, I'm not as sure that is the ripest playing ground for machine learning. So to this issue of design time and runtime, CAD traditionally concentrates on design time, but I think that optimizing system behavior at runtime is getting more important by the day. First, we see lots of very significant variation in use cases. We see the same components used for different things. We also see variation in the types of data that individual users deal with. And of course, we also have to deal with variation from component to component as well as aging. So even if we have a perfect snapshot of a device at time T1, at time T1 plus epsilon, it's no longer entirely valid. So this is in part an architectural issue, but I'd like to hear some thoughts as to how it plays directly into the CAD process. Certainly more complicated architectures that support runtime tuning as well as runtime data collection are just more complicated, right? But are there other issues in the design flow that need to be taken into account and can be, so this is an issue of both how do we use machine learning and also how does the downstream applications to machine learning affect our system design methodologies. Okay. Several panelists have talked about data ownership as a big problem. I agree. I think that's a big concern. I don't have a full answer. It's in part it's not entirely a technical issue. I keep hearing lots of people saying that we're flooded by data. We have all sorts of data and our only problem is figuring out what to do with it. I'm not so sure. I mean, because I don't think we always have the data that we're actually interested in. Certainly, we have lots of data about kittens and puppies. We have too much data about the personal grooming habits and fast food preferences of hundreds of millions of individuals. However, for lots of problems like the environment, manufacturing, public health, we have perhaps not exactly all the right information that we want. Okay. So I think that CAD is an illustration of that observation, right? We don't have all the data we would like to have in order to apply machine learning to our problems. And of course, this goes not just for design time data, but also collecting data from users about use cases that can be used to optimize designs. So, there's certainly a business question here, a legal question. Can the science of artificial intelligence help? I don't know. I really don't know. One would hope that improved training algorithms would need less data or less raw data at least. But I think that's a significant challenge, not just for CAD, but for machine learning and artificial intelligence. And finally, variation, right? So we know that components within a given part number vary. And of course, they vary over time also as they age. How much does this complicate training? And I think that the work that my friends at Karlsruhe and I have been working on about temperature estimation is one example of that. We're not yet sure how well this will generalize. And we also need to be able to generalize, not just make sure that our training works for all the different corners of a given part number, but also from one part number to another. If we have to take apart systems and run hero experiments on every given part number in order to achieve adequate training results, then machine learning will be useless to us. So those are my random thoughts. Thanks.
Thanks very much, Marilyn. Was very, very, it's triggered many thoughts at my end. So I hope, I'm sure that also with the audience, we'll see with the question. Our last speaker is Avi Ziv, and he also comes from, not only comes from Israel and from IBM, but also from the verification world, which is, as you heard this week, less presented in this community, which I certainly hope that it will be more and more represented here. So Dr. Avi Ziv is a research staff member in the Verification and Quality Technology Department at the IBM Research Laboratory in Haifa, Israel. Since joining IBM in 1996, Avi has been working on developing technologies and methodologies for various topics of simulation-based functional verification, including stimuli generation, checking, functional coverage, and coverage-directed generation. In recent years, the main focus of Avi's work is bringing data science to hardware verification world. Avi received the BSc degree in computer engineering from Technion Israel Institute of Technology in 1990, and the MSc and PhD degree in electrical engineering from Stanford University in 1992 and 1995, respectively. He's the author of more than 50 papers and the inventor of more than 20 patents, mostly in the area of functional verification. And Avi, stage is yours, and please go ahead and ask questions, everyone in the audience. After Avi, we will open the room for the questions. So Avi, stage is yours.
Thank you, Raviv, and I hope you can see my screen.
Yes.
Just a picture, and this is not IBM site in Iceland, but just picture from Iceland, place that we hoped to be in, but couldn't come this year. And it's good to be the last speaker on the panel, because all I can say is I agree with everything everyone ahead of me said, and then finish and let you ask the questions. But let me talk a little bit about the perspective of functional verification in the area of ML. And so the big question of this panel is, where is the treasure hiding? And I can say, and we heard about it a little bit even today, but also yesterday in the keynote, there are places where machine learning is being used in verification. It's not a lot, it's very sporadic, but it's being used and it's giving benefits. For example, again, examples that were given yesterday, tuning engines of formal verification tools, finding the right reduction to run when you're doing formal proofs and so on. Building regression suites in order to optimize the simulation work. And there are other examples, but as I said, they provide nice improvement. They help the verification team. They improve the quality of verification, but they are not the big treasure. So if we look at where the real treasure is hiding, it's probably places that are very deep, very hard to get. And those are the places where two main bottlenecks that of manual work that still required in verification that is very, very highly automated in this world. They require a lot of expertise, but also a lot of time and a lot of trial and errors and so on. And those are the areas of coverage closure. How do you get to hit the coverage events that you put in your design, and you want to hit them to make sure that your verification is thorough? And the area of debug and triage. And there we see, and actually for many years, and my maybe first work with machine learning verification that started more than 20 years ago, before machine learning was so popular, was trying to work on coverage closure with machine learning techniques. We published a lot of papers. There are others that published a lot of papers around this time, but nothing could really solve this problem to get to something that can be used in tools today. And the same thing can be said about debugging triage. So why is verification so hard for machine learning? I think that first of all, if we look at the world that we are living, and this is probably going the icons that I show now in from the least significant to the most significant aspect. We see that we have our user are highly skilled and they are really experts in what they are doing. And therefore, if you try to build decision support systems, they need to be of the really highest quality, because otherwise you will show them what the system is saying, and they said, oh yes, we know that, and we have some experience. We designed a system that look at the curve of bugs that you find and try to identify significant events that happening during the process. And it ran and it identified every few days. It says, oh, here we have some change in the trend. We're finding more bugs or we're finding less bugs than we expected to find. And you go to the verification lead and ask him, is this, what do you say about it? He says, yes, this is correct. What you're doing is correct. But I know this doesn't help me. So you need something that will be really high quality to give them, to surprise them, to help them really with things that they do not know. The second thing is that verification, and specifically dynamic verification, simulation-based verification, is very chaotic world. Actually, if we look at what verification is trying to do, we're trying to do that every test that we run will be completely different than every previous test that we run, because otherwise it's useless. If it's going to do the same thing that previous test did, it will not help us reveal the bugs that we didn't find. It will not help us reach coverage that we didn't find. So we work very hard to make our generator be very random, generate completely different things every time they run, and therefore trying to do things like, I don't know, anomaly detection, another field in machine learning is doing very well in, will not work, because every test is an anomaly if you compare it to the rest of the test there. It's also we're dealing with the world that is continuously changing. So if we work with our design, then every day we get a new model and things are changing. We fix bugs, we create new bugs. So if we build a system that knows how to try to classify bugs according to a common root cause, the common root cause of yesterday should no longer be seen today, and we should look and find a new cause. So these things make machine learning hard for verification. And finally, the problems that we are dealing with are not traditional machine learning problems. And again, I think that, or not, we heard some of the previous panelists talked about it. But let me give you some example. And this is something that maybe one of my biggest contribution to the area of coverage directed generation is this slide. So if we look at the traditional machine learning work, we know very well how to build classifiers, and we have classifiers. We build and train classifiers on dogs and cats. So if we feed a cat to the classifier, it will give us a cat very nicely. If we feed a dog, it will give us a dog, and again, very nicely. And we can build those very efficiently. They will do the training. They will do the classification with very high accuracy. But what happened here? We want to deal with events that we haven't seen before. We want to cover those. This is the important. So we feed a zebra to this classifier, and this classifier haven't seen a zebra before. So what we expect it to say, and it's true, machine learning people deal with that. That's called one-sided classification in many places. But if we think again, our problem is actually a little bit different. What we really want is to tell the machine learning system, dog, and then let the machine learning system that was trained on dogs and cats think about it and give us a picture of a dog that it's actually have never seen before. And actually, this is also something that the machine learning people worked about. This called in some places diagnostics. In other places, I think it's more common these days is generative models and not standard classification or regression. So this is something also that machine learning people are dealing with. But what we really try to do is take this classifier that we trained on dogs and cats, tell it zebra, and expect it to come with a picture of a zebra or the test that will help us hit the zebra coverage event that we haven't seen. And this is something that machine learning, traditional machine learning, is not dealing with. So on Monday, again, Raviv gave some approach that we are dealing with, which again go back to one of the previous panelists who says that we need to combine machine learning and other algorithms. So we combine machine learning and optimization techniques to do that, but this is not traditional machine learning. So going very fast to the questions that Raviv asked. Do we simply need more time to identify problems? I think no, I think that we know what the problems are. I think that we also know in which problems machine learning can change the game. The problem is that for many of those problems, we don't know how to solve them yet. So is it a matter of finding the right machine learning means for CAD? Yes, but I think more precisely, there are some questions that I think we still need to find if machine learning technologies can actually provide the answer, or how to combine machine learnings and other means, and or what should we do to help machine learning, like I don't know, design for verification that will take into account the fact that we use machine learning for the verification. Are CAD problems fundamentally hard even for machine learning based solutions? I think that some of them are not, but of course, those that are, and definitely those that are and should have a big impact, are the ones that we are looking at to try to find the solutions. Is it difficult to improve an already highly automated area using cutting edge technology based on many years of research? Again, I think I touched it. Yes, it's hard because we have these highly skilled people that are also, in some cases, tend to be very conservative. So you need to really convince them that you have something good before they will be able to use this. With most of data owned by chip companies, is data availability a major blocker? So I think it's yes with capital letters. The problem of data availability is very problematic because, for example, it's very hard for us to collaborate with university because we can't show them our data. And they have to work on some small examples, on some old examples, and so on. But on the other hand, in a lot of places, even the internal data within IBM between one project and another is not really relevant. So we need to try to see if we can find some metadata that we'll be able to share, and then tune the algorithms to the specific data that the specific project. And finally, are domain-specific optimization that require further advances in machine learning? I think that the answer is yes. And again, going back to the nice views of Iceland, and thank you very much.
So thanks a lot, Avi, and thanks a lot to all the panelists. And I would like to ask all the participants to come up and ask and join and ask questions. You can unmute yourself and ask yourself. You can write the questions in the chat of Zoom or in the Slack channel. So we have one question coming from Tom Lucas in the Slack channel. Question to anyone. Given that DRC is normally a precision calculation with maybe some small tolerance, is MLDRC seen as only augmenting rather than replacing algorithmic DRC for reason of performance, or is it good enough? I suppose in general, what is the connection between precision and estimation? Please unmute yourself and go ahead.
I think Tobias also asked a question at the Zoom chat, right? So I'm not sure if that's related, but I just want to clarify. So in our work, when we fix the DRCs for standard cell, internal standard cell routing, we don't, the DRCs are still tracked by conventional algorithms. We didn't use ML to track DRCs. So we have some in-house tool that's able to do a faster DRC track based on basic grid-based layout. But it's still algorithm-based, and then basically the machine learning is in actually trying to fix it, right? So we're alternate, changing the layout, modifying the layout to fix the DRCs. So I think the issue he posted on a Slack is oh, sorry, I think that's different person. Okay, sorry. Yeah, about the DRCs, whether ML can use to predict DRC. I think the Francis group at the NCSU did some work in using the machine learning to predict the DRCs. And I think that's very interesting. I think if you look at the maybe the Foundry, they when they track DRCs, they also use a lot of statistical approach. I think because they have to look at a lot of layouts to figure out how do you summarize the rule, right? It's like a manual process of creating rules. But maybe you can use machine learning to help. Maybe they're already using machine learning to help them to generate these rules. Yeah.
Yes, so let me kind of give my take to questions. So if you look at actually DRC, right, it's something that you call is a sign-off, right? And so there's zero scope, right, of error. You pretty much need to have 100% accuracy. So as such, the mainstay of it is going to be algorithmic approaches, actually, as Mark mentioned. But again, if you can imagine actually there can be algorithms which can kind of help you quickly, for example, using, for example, some kind of neural network model out there, right? Kind of zoom into a lot of issues. So during initial design iterations, but the final sign of always has to be algorithmic. It has to be 100% precise. And this actually in general kind of comes to sign off, right? So for example, if you're building a formal tool, you cannot say that, that you have, or a simulation tool, right? That you have your outputs accurate with 99% or 99.9% probability, right? To the extent we can, we need to kind of engineer these, right? To be 100% accurate. Of course, there's nothing to say that, that each of these tools will include a lot of heuristics internally, right? Which different algorithms to take, or, which paths to analyze. And ML can kind of play a great role in that, in kind of building these tools better. But the final sign-off will require 100% precision, and I think 100% accuracy, and that needs to be pretty much algorithmic.
Right. I agree with both Mark and Manish. Just to add a little bit, right? So yeah, definitely, I think the final sign-off, I think, need to be exact, right? But you can use some early stage, let's say during placement or routing, you can kind of predict what could happen in the DRC stage. If you end up, you will have a lot of errors, so you can kind of mitigate that during early stage, right? That's what I think the ML model will provide a lot of value, right? And even let's say for the lithoGAN that we have worked on, right? So those kind of things, right? I guess it again can provide some kind of prediction. It can be used for early like design, right? But you know, the final sign off, you know, I guess you know, you're talking about many millions of dollars NRE and stuff like that. Right? I think companies probably still want to do you know, more accurate models, right? Thanks.
Thank you. So let's move to the next question coming from Asma. Just a second. A pop-up blocks me from reading. Go away, pop-up. Thank you. What sort of ML advances needed for CAD that are not needed for other fields? Avi, this is your zebra. Yes, go ahead, Marilyn, yours.
Again, I'm not a big machine learning expert, so I cannot say that anything that we are doing for CAD is something that has not been done in other places before. But again, looking at my example here, this is something that definitely it's not something that gets a lot of attention from the machine learning community. How do you work on something that both you want to go on the reverse sides, on the generative side, and you want to do that for places where you don't have the evidence in the training set is one thing. I think that the other thing that, again, I mentioned is the fact that how do we deal with data that is actually continuously changing on us, and we try to maybe, I would say, train the model building to build and to know how to take what to take from the past and what not to take and so on. I think this is something else that machine learning is not working a lot on. And I'm sure that in other domains, there are other places, other fields, other problems that are not currently dealt by the machine learning community.
Yeah, so I think that I think actually that's there are a lot of nice tools that you can kind of borrow, you know, from this ML advances, right? I mean, I think that you know, your convolution neural network for vision or advances in deep reinforcement learning, for example, right? And or you know, a lot of recent advances in natural language processing. So I think, for example, in my group, we borrow all of these different techniques. But when you look at the final algorithm that needs to be done, right? I don't think that there's any parallel to the algorithm, to the way you adapt these algorithms to the problem, right? You want to do an OPC mask generation. I think so. The final stage in the application and how do you kind of, you know, the alchemy that you use to generate this mask, that's obviously going to be unique to EDA. But I think that the more I think the EDA community is actually aware of the advances being done in ML and AI in these different fields outside, right? I think that the more we'll benefit from it.
Oh, I have a couple of observations. First, I think working around our limited access to proprietary data might be one area where new theory or improved theory might help. I think that a lot of machine learning right now is oriented towards, should we say, batch processing, you know, classify this, classify that, whereas we deal with both time series data and highly spatial data. And I also think the huge volumes of data that are required to analyze a design really pushes the limits for a lot of these machine learning methods.
Yeah, I just want to add that so traditionally machine learning, especially the you know, like the most eye-catching advanced maybe in the last few years are about the perception, right? It's a perception task, and then you know this you know, control, which is basically optimization task, right? So I think optimization task is getting, you know, like getting popular in the machine learning community, but I don't think it's mainstream. It's not like a mainstream, right? So so I think the, you know, in the even the more optimization they done in the machine learning community, it's sort of high level, right? So, but in our case, we have very detailed optimization task, and has a lot of constraints, right? And a lot of these constraints are also very difficult to describe. So, so I think basically we need to efficiently have some, basically we talk about the representation, data representation, right? We need to be able to represent our data, which includes the design data and the design constraints and all the, all the constraints. And then, once you can represent these things efficiently in your networks, and then we can talk about optimization, right? So I think these are just the kind of things that are unique in our case.
Yeah, I think so. A couple of things actually that again that has not seen that much attention actually in this EDA world. For example, as Marilyn mentioned, right, we have time series data, right? If you look at actually verification traces, right, simulation run traces, that's exactly time series. Again, to Mark's point, for example, this for example is pretty common, for example, in recommendation systems, right? But for example, ML algorithms that work on graphs, right? So that's again a pretty big deal actually for in the EDA world. A lot of our data is in form of graph. So I think that it'll be great to see more research and bringing in more of these ideas. Some of these are fairly mature outside of EDA to kind of bring these into the EDA world, and these will have applicability, I think, across multiple EDA algorithms.
Yeah, I just want to add a little bit to Asma's question, right? So yeah, indeed, right, I think I agree with what Mark and other folks also already mentioned, right? So indeed, right, in CAD, there are some specific problems that the mainstream machine learning people really don't work on that much, right? So, like all this, design hierarchy and the timing, this graph, you can say use some kind of graph neural network, but then we also have timing and other, design constraints, right? So I think ultimately, let's say, right, so we probably need, this kind of problems still need to be solved by our community, right? Borrowing the ideas from the machine learning bigger community, but ultimately we need to kind of digest that and then, enhance and adapt to our applications, right? Okay. Actually, I have a quick question for Manish. I don't know, I know there's some questions from the audience. Can I ask you a question?
Sure.
So in your, so this is related with data, right? And also the model trend using vendor data or something like that, right? So according to, so currently what's the industry's general practice? Do the vendors own the model, or you guys can also leverage some of the models that you learn from there and enhance your product? Like when you work with customers, let's say like a more conventional machine learning, right? So you work with customers, you enhance your tool, you can put it in your next release, stuff like that, right? But for machine learning models, is that the kind of forbidden area?
So I think so. So it really depends. Actually, we see application. I think that we see all different variations. So, for example, when you can kind of imagine actually that you take kind of a trained factory model, right? So, for example, we train model, for example, using all the data that we have internally in-house. We ship that to the product, and then what can happen actually is that you can kind of train this and further fine-tune this, right? Based on kind of customer data, you do kind of a transfer learning where you kind of adapt this to any verification methodology specific stuff or their design specific stuff or there, right? So the bigger challenge is actually that, can you kind of get this data back? Can you get all of these parameters back, right? And if you get all the parameters back, sure, you can kind of ship an ensemble model in your next rev. But what would be more interesting is, can you get the training data back, right? And then all of these are kind of open issues that we have. We see a great variation of a spectrum, right? So I mean, if you just have a big matrix or collection of matrices of numbers, some companies are okay, right? And that there's nothing really proprietary in there. But I think that in some, there's also a question of competitive advantage, right? I mean, are you kind of letting go of some data that makes your competition stronger, right? Because ultimately, the faster the tools can run, or the higher accuracy it can give, or better debuggability, right? In effect, you're kind of helping competition. So that's a question actually that really That was a question that I kind of raised in my last slide. And we really need to have some kind of standard practices out there, or generally accepted practices, so that we can all think how to advance the field as a whole, rather than have silos in which data and models exist.
Thanks. I would like to add a question here, and let me try to take you a couple of levels down to some of the problems that data scientists face. And it relates to the assumption that we have huge amount of data. And the problem is that in many cases, we have lots of data, like traces in the design and logs, but it's not easy to understand how to use it. Taking it as is a mixture of is a mixture of noise and signal. And if we try to find the signal with so much noise, sometimes this is the main problem, and data is not generic. So you go from one tool to another tool and you get another format. So I'm sure that you're familiar with this problem. How much do you think this is blocking, and how much change in the tools maybe to generate the data, instead of fixing the data after it was creating it more machine learning friendly is a key here.
Okay. No, actually, by the way, a great question, and I'll since I deal with it so often, let me kind of jump in first. So, by the way, so I think that if you look at it, actually, EDA, right, and EDA is a very specialized business, right? Every tool has its own characteristics and their own kind of data out there. So, we need people, and we have seen people who do best at this are the methodology experts who also understand to some extent, also to some extent who are data science experts, right? So these are people who have a deep understanding of the problem domain or the specialized niche of it. They can take the data, wrangle it, and then they suggest, that this is what the data that we already need. And this actually, as you can imagine, right, it needs a tremendous amount of experimentation and seeing, what kind of data works, what needs to be extracted out. And I think that I've seen almost no project that works right the first time. Is the second or the third attempt at building up these ML algorithms, or putting in the right approach in the problem that kind of works. So it requires both domain expertise and a deep understanding of the data and methodology to fix this right. And Raviv, you're absolutely right. I think that you need to generate data. The easiest way to generate the right data from start. And that only comes through trial and error and experimentation and analysis.
Yeah, so just to add on that I feel like machine learning for EDA is kind of between data science and deep learning or machine learning, right? Because we have to generate our own data. So I think that the disciplines, like the techniques that people use in data science should be very useful and actually absolutely necessary in our case. So usually in the data science project, usually 80% or maybe even more of the work is actually just processing the data, right? Like make data clean, feature engineering, and so on and so forth, right? So that's like the main parts. And if you compare to like other domain like vision or language, or that part is missing, right? They don't need to do that. It's because basically all the data sets is there, and it's already done. So I would highly recommend to all the people, everyone doing machine learning for CAD to really get the foundation of data science. If you don't have that, learn it and practice that. And that's like, a threshold, right? If you want to be successful, at least to get that threshold out, right? Like be able to do this data science things yourself and get feature engineering work and clean your data and beyond that, then you can talk about the models. Yeah, I think that's my point.
Marilyn, go ahead.
So I think there's always a tension between doing AI and using AI. And I'm an inventor and I'm interested in solving a problem, then going on and solving the next problem. So I naturally lean toward using AI. And I think that CAD companies, unless they want to change their business models fundamentally, are pretty much in the same position. So as an inventor, I'm always skeptical of using zillions of CPU cycles to relearn something that we already know, right? So it seems to me that in order to improve CAD, we need to use machine learning judiciously, apply it where we can't do it any other way. And to the extent that we have algorithms that work, we shouldn't throw them out.
Thanks. Avi, you wanted to also?
Yes, again, I'm going to say, I think that, again, at least in verification, we may have a problem that we have too much data, that it's going to interfere with our attempt unless we know what to look for. Just throwing all the data and let the machine learning do the magic will not work. We need to understand what feature may be useful and what not. And there is a big risk there because we may miss very important features that will help us solve the problem that we're trying to solve, but because we don't think they are relevant, we'll not put them in the mix. So I think that, again, feature engineering is one of the biggest challenges on how do we take the data, how do we get it to something that the machine learning algorithm, whatever algorithm we are using, can benefit the most out of it. And I think this is a big challenge for the CAD community.
Okay, so I think we reached the end of our time. Hosam, do you think that we can take another question or should we stop here?
Well, I mean, one quick question does not harm. We always have time for one quick question.
Okay, so I'm sorry, we have 3 questions that were not answered, but we'll be able to continue our discussion in the Slack channel afterwards, but I will pick randomly. So I will take Lorenzo's question. So do you think that hierarchical reinforcement learning, where you have different levels of rewards for design, maybe at components and then a bigger design level, could be a promised direction in ML4CAD?
If I knew the answer to that question, I'd be talking to you from the beach and not from this hellscape.
Okay, I'll try to address a little bit. So since I work on reinforcement learning, so maybe you can sort on it. So I think that both hierarchical RL and like distributed RL and multi-agent RL, and all of this is the like a new frontiers of reinforcement learning, and definitely I think we should try that. And one thing I want to bring up is like in hierarchical RL. When you have multiple multiple RL doing working on different levels, right? So I think don't restrict ourselves. Just think about, okay, it has to be each level has to be a RL, right? A machine learning agent, right? It could be a traditional algorithms, right? So when you construct your hierarchical system, some of the layers or some of the agents, some part of the systems might be conventional algorithms. Because they're doing a good job, right? Just keep it. And then, you just leverage RL in the area that the conventional algorithm doesn't, do very well. And then when you compose the whole system, that might be doing something that, we couldn't do before. That's my point.
So I think a couple of things actually. Hierarchical certainly seems like an interesting area, but I think as Marilyn and Mark have both mentioned, you know, if you have algorithms for working well, then don't give up on it, right? And so you can think of actually, a hybrid system where you have both RL and combination of RL and algorithms working. But I think that the more important to this is, what is the problem that you're trying to solve? Are you trying to solve the problem of actually global routing, or is it kind of detailed routing, mesh routing? So I think it'll be more important to start from a problem perspective than to start with hierarchical RL as something that you want to do, because I think that as all the panelists, and I think a lot of these talks have said that these are all hard problems, right? And trying to take some of these problems and then trying to see which algorithms or a collection of algorithms can help would probably be a better place to kind of start with and seeing what works well.
Yeah, I agree, right? So I think if something is already working, right, so we should definitely steer those algorithm-based approach versus data-driven, AI machine learning-based approach, right? I think ultimately our goal is to really solve the problems, right? So I think it's important to identify the critical paths, right, where in the current design flow where the problems, right? Once we identify those problems, right, then try to find the best of the both worlds, right? So this analytical or this algorithm-based and the data-driven based, right? This explore and exploitation, right? So yeah, I think okay, yeah, that's my view, right, as well. Yeah, thanks.
So I feel that we could continue talking and discussing for several hours, and maybe if it was a physical event, then we would go now to the best restaurant in Reykjavik and continue our discussion with a glass of wine. But I would like to thank the great panelists for very inspiring thoughts. Thanks, Mark, David, Manish, Marilyn, Avi, and thanks for the audience for the questions. Not all of them answered, but I hope it was an interesting to you as at least as it was for me. And Sam, I will let you lead the next session, our last session actually in this year.
Thanks, Raviv.